Hi, I'm Miguel. I have an interest in networks finance and obviously Python, and I'm going to bring these together and talk to you about this. So, just a short bio, I do work in finance. I've been working in financial services since a couple of years now. And, but my background is in robotics and computer science. So in the end, I kind of tend to like different things than my colleagues do, and I try to model things differently. And sometimes I like networks, as you will see, and I get into interesting conversations with colleagues, and they keep pushing me into trying to figure out why it is that what I find interesting actually works or should work. In particular, I'm interested in the applications of network theory to risk management. Now, please be aware, I really love networks, and I could speak about them a very long time, but I'll try to keep it short. And if you have some questions in the meantime, I'll be glad to be interrupted. Now, why do I like networks? Wait a minute. First of all, basic criteria. They give us a way of reasoning about concepts that are very intuitive and a very formal way of reasoning about it. So I can say, intuitively, Frankfurt Airport is an international hub, and hub will have a meaning in network theory. I can say that Ebola is a contagious disease, and using network theory, I can use network models to model this contagion process. And I can also say, and back to finance, Lehman was simply too central to fail. And what does central mean? Networks, you can model structure with networks, and that will be very close to graph theory. You can also model processes in networks. Today we're going to focus on the structure, be very near the graphs. And the reason why I wanted to do this is because like networks are a bit like the metadata for the NSA. They sound uninteresting, but they give you a lot of information. Now, from an organizational point of view, you can look at the network structure. In this case, some companies, some of you might have been there, might disprove what is being shown here. But they tell you a lot about how it is that the organization is working, and you just have to look at the picture and have a feeling for what it is how do people interact inside of these networks, inside of these organizations. From a strictly financial point of view, this was very hyped after 2008. Already aggregated data at the country level gives you an idea of how things hang together. So we can see from this graph that you have like a core periphery structure. And this is already some information that you get just by plotting the graph. Now, in the aftermath of 2008, there was a lot of regulatory, and there's still a lot of regulatory activity. And one of the outcomes of this regulatory activity, both in the US and in Europe, was that certain derivatives contracts had to be cleared centrally. What it means is that if I'm a bank and I'm trying to do a deal with another bank, and this is a qualifying contract, then I have to go to a third party, and this third party will assume this other person's responsibilities towards me and my responsibilities towards this other bank. So in the instance, what you're doing is you are transforming the structure from a highly connected to a more like hub-connected kind of way. So this is simply just looking at the structure. Now you can ask yourselves, is this a good change? How does it affect the processes that use this structure? But today we're not going to go into this. Now another usage is, and this is, I'm just copy-pasting from a paper, this is, people have shown that if you go to a stock exchange and look into the relationships between counterparties, these relationships being buy and sell, you can try to see whether interesting patterns occur. For example, the patterns below, they call motifs. They are a very sure indication that maybe trading manipulation has occurred. So again, structural information helping and try to give you a sense of what is going on inside the network. Now, this is a current research topic of mine. I'm not going to say much about it. And what I'm trying to look is into credit portfolios and try to see whether dependencies between obligors, so people you have lent, or people or institutions you have lent money to, whether the connectivity between these institutions is actually a factor that you should model or monitor or not. And what I find very interesting about this is just by looking at a large portfolio of institutions that you have lent money to, and looking into equity structure of these institutions and plotting the relationships, the equity relationships, like company A owns stock from company B, you have a sense that there is a very connected core of companies, and the question is, am I really taking into account all the risks when I am lending money into these companies? So I'm speaking a lot about graphs and networks. For me, a graph is this mathematical object. A network is something interesting, or a graph that endowed with some context and some meaning. Now, in the essence, you have some vertices, or some nodes, and some edges, which are the connections between these nodes. In the course of the rest of this talk, I'll be using a lot the term adjacency matrix, and these are simply the weights that you have, plotting the weights or the connections between each of the nodes in the matrix form. We speak of undirected graphs when this adjacency matrix is symmetric. We speak of unweighted graphs whenever the adjacency matrix either contains zeros or ones. It is directed when the adjacency matrix isn't symmetric anymore. That is, A being connected to B does not mean that B is connected to A. And when the connections can be different, so you can assign, for example, a weight to it. So let's move away a bit from finance. And one interesting thing so we've been talking about structure, and the structures that I've shown you are some things that you measure directly from the system. Now, it would be interesting to see whether you can use some implicit structure in order to get information out of the system. Now, if you think of clustering, so going back to the very different direction, if you think of clustering, and if you use, for example, this 2 moons data set, now there is a clear structure to it. You can see it. But if you use, for example, very naively, if you use the k-means, there's no way that you're going to capture this, because k-means assumes that the world is built around centroids in this space. So whenever you do the clustering, even if you know the right amount of clusters, it will find the clusters maybe in areas that you wouldn't be expecting. Now, one way to go about this is use the local structure of data, so that you see all the points that you have in your data set, and you try to see which points are near this particular point and which points are far away from this particular point. So near and far also being able to be some very broad definitions. It doesn't even have to be a metric space. Now, in spectral clustering, you use this. You take a whole distance matrix between points, you sparsify it using some locality criterion. And then you cluster something called the Laplacian matrix. The Laplacian matrix is simply the adjacency minus a diagonal containing the degrees. Now, the eigenvectors of this Laplacian matrix are very, very interesting. And this is what is being exploited in spectral clustering. Now, it's too early in the morning still. I'm not going to go through this. But if you take the similarity matrix from this 2 moons data set, you can kind of already see some of the structure if you use, for example, something like a dendrogram. And if you use a locality criterion on the similarity matrix, and you plot this as a graph, and this is what I've tried to do here, you can see that this structure is getting very near to the original structure that we want to have. Now, when we take the Laplacian of this one, and we do the eigenvector analysis, it turns out that the low-value eigenvectors give you actually the low-value eigenvalues give you the eigenvectors that will be able to separate these areas. So, for example, if we know that it's 2, but let's just make it not work so well. With 3 clusters, then you get at least one of the moons pretty well recognized. So let's go back to finance. Can we use something from this locality analysis? Can we infer structure from, let's say, correlation matrix? Now, correlation matrix and covariance is a very, very usual way of modeling time series data. In essence, what you do is you take a time series, you take a given window, and you compare each of the time series by a correlation measure, and then you put this together, you put this in a matrix form, and you get the correlation matrix. Now, this correlation is computing by using the returns. The returns are the ratios between the end-of-day prices of given assets. You usually normalize them, compare the pairwise correlation, this being the Pearson correlation. And when you do this over time, when you get this correlation matrix over time, then something interesting happens. If you do the eigenvector analysis of this correlation matrix, put it a bit, and then you plot each of the eigenvalues over time, the blue one here being the strongest, the first eigenvalue, you see that whenever something interesting happens, and interesting might be endogenous or exogenous to the system, then you get some spikes. Right? For example, Lehman, you get a huge spike. The housing bubble, even some important people talking at a press conference, Mario Draghi at ECB, the whatever it takes. The downgrade, Fukushima. So this is really interesting information. Now, people are using this, for example, to make something called risk on, risk off. So whenever the first eigenvalue is rising, you call this as a risk. I don't remember. Risk off? No, risk on. So everybody is kind of synchronizing. Everybody is doing the same thing. So the first eigenvector is very strong. That means that sorry, either things are very correlated or very anti-correlated. So kind of everything is moving either in the same direction or in the opposite direction. Whereas when you have a risk-off phase, you have more diversification, and then the first eigenvalue just drops over time. Now, this is very interesting from a purely descriptive perspective. This is interesting. But the question is, can we do something with this information? Now, what I'm going to talk about is I'm going to do more of talking about a paper. It's not my work, but I find it very interesting, and I've been trying to replicate parts of this work. And what they use is actually, what they do is actually try to use this information in order to do an asset allocation decision. That is, they try to use this information in order to invest. And their whole reasoning is a graph-based reasoning. And that's why we're talking about here today. And they're using basically the notion of centrality to code diversification. So this is the paper. It's a Nature paper. It's very, 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 very cool paper. So what do they do? For each point in time, they look at a given set of correlations from a fixed set of assets from the past, build the correlation matrix, and then select from this pool of assets, select a given subset of assets. If you, for example, you're based on trying to trade on the, for example, S&P 500, you're not going to put 500 orders every time. You're not going to reshift your portfolio every time. So you want to keep the number of assets that you're trying to manage actually very short, so that the costs associated with the management of your portfolio are reduced. Now, there's several current ways or usual ways of doing this. For example, one of them is using sector analysis, for example. If you know that you have a large pool of assets, and you have some financials, you have some pharmaceuticals, you have some automobile industry, you have some web companies, you're not going to put everything in the web companies. You're not going to put everything in your car makers. You're going to try to diversify a bit. So you're using a prior information in order to make a deformed incision. Now, what people have shown in time is that if you take the correlation matrix, if you do a cluster analysis on this correlation matrix, then what you get sometimes is clusters that are very similar to this sector information. So, and if you do a graph analysis of this correlation matrix, then you get also clusters that are very similar to the information that you already know about the category. So this is another hint that the structure of the correlation matrix might have some interesting information, and you're already using it. So, but back to the methodology. So for each point in time, they look at the correlation matrix and try to decide in which assets am I going to try and invest now. They have a different set of methodologies. And then they evaluate the portfolios that they've built with these asset baskets over time. Sorry. Now, as I said before, the correlation matrix, you need some structure in order to interpret the matrix itself. So if you just plot it using the lexicographic order of the ticker names of the assets, it's going to be difficult to read. It's difficult to see something out of it. If you use a dendrogram, then you start seeing some patterns. Now, the dendrogram is nothing else but a tree, right? It's a tree structure. So a tree is a subset of a graph. There I am again. There am I again, making the connections to the graphs. And then the question arises, do I need every single data point in the correlation matrix? Do I need to model? And if you look at the tree, then the answer is obviously no. Now, which criteria should I use in order to remove information or remove data points from my correlation matrix to specify my correlation matrix so that I get some parsimonious representation of it? Now, there's a whole set of criteria that you can use. You can use a threshold-based. You can use like the probability that some correlation occurs out of the random. You can use random matrix theory, but you can also use geometric criteria. One of the geometric criteria is, for example, the minimum spanning tree. Now, the minimum spanning tree tries to go through all the vertices, through all of the assets, in a tree-based structure, and trying to minimize the whole distance, so the sum of the weights of the edges. Now, what we have here is the minimum spanning tree of the correlation matrix that I've shown. And you find some sector-based information here as represented by the colors. So you see that they do try to stick together things that are similar. However, you throw a lot of information out when you do the minimum spanning tree. Maybe you need more information. So now what the people in the paper have done is use another way of constructing a graph out of the correlation matrix. It's called the planar maximally filtered graph. And essentially it uses something called the planarity criteria, which is simply a yes or no test. And if yes, this means that the graph can be embedded into a sphere without edges being crossed. So this is a plain geometric criteria. Now what they do is they take the similarity matrix. They go from the highest similarity to the lowest similarity and try to add edges to the graph. If the graph is planar, then you keep the edge. If the graph is not planar, then you throw the edge away. What comes out is a graph that has the minimum spanning tree in itself, but also has many more connections there. Now, what they use is this way of building the graph. So this is a picture from the paper. And they reason about what is central and what is peripheric. Now, why would you do this? Now, the idea is that if something is central, then probably it is similar to a lot of things nearby. Whereas if something is on the borders of your graph structure, then probably it is farther away from a purely similarity perspective from most of the other points in the graph. So what they do is they rank the whole set of nodes based on the similarity, and they take the 30 less central nodes, and they try to build asset baskets from this. So they have a correlation matrix. They transform the correlation matrix into a graph. And then they build a centrality measure, which tells them this is in the middle or this is in the periphery. And they say that whatever is, if I take assets that are in the periphery, then I'm probably more diversified. And I find the results very interesting. Now, if you take sets of assets using peripheral assets, which would be now the red squares, or you use a purely based performance criteria, which is the triangle, the pink triangle, or if you go to the center of the graph, or you pick some at random, then you get different, in average, you get different portfolios. What is interesting there is that for equally weighted portfolios, the peripheral assets, they outperform the market portfolio, which is a good sign, and they outperform every other. Now, at the same time, they have figured out that the performance of the assets isn't correlated to the centrality. So using equally weighted portfolios, they perform pretty well. When they put some optimization on top of it, then the market portfolio being every 500 assets, it's only here as a control. For small values of for small sizes of the baskets, it outperforms the peripheral portfolios, but even for larger asset baskets, then the peripheral portfolios tend to outperform it. Now, what is very interesting as well is that the weights given by the optimization for the peripheral portfolios, they are pretty small. And this is something that is usually addressed in the optimization in the optimization of portfolio management, and this is a very, very interesting property for portfolio managers. Now, at the same time, the central portfolios tend to be less performant, again, even if there is no correlation between centrality and performance of the individual assets. Now, what I'd like for you to take home as a message is, first, structure is important. And network theory helps you deal with the structure. It helps you identify groups in your network, and it gives you precise definitions of what is central. And this, we have seen, this is information that might be useful even in the case of financial modeling, even in the case of investment. There is lots of structure to be seen in finance. Now, for example, when I look at yesterday's talk on the size of banks, now this is very obviously very valid research, but it's not the only way of measuring. Measuring the size of banks is one thing. Measuring the importance of banks is another thing. And in order to measure the importance of banks, you both need to measure the size and the place of the banks inside of the system. And so you need to do a structural analysis. So additionally, even if you don't have the structure being given to you by the problem definition, you can try to infer the structure by using local methods. For example, using these minimum spanning trees, these planar graphs, or, for example, using spectral clustering. And that's it. I'm open for questions. Thank you.